So our last speaker in this session will be Professor Daniel Malinsky from Columbia University. And Dan is an assistant professor of biostatistics in the Mailman School of Public Health. And he will be talking on causal determinants of post-operative length of stay in cardiac surgery using causal graphical learning.
Good, yes. All right, thanks very much to the organizers for putting this together and for having me. My talk is going to be less directly fairness related than the previous talks, but since the previous talks all rely on, in some way or another, knowing the causal structure, the causal graph or causal relations between things in order to modify some downstream procedure, my talk is really going to focus on the sort of applied work of learning the causal structure in a domain in which we are uncertain about how things are actually working. And we were, in fact, actually motivated by some fairness considerations when we started this work. So we were working with a group of heart surgeons, cardiac surgeons, and who are interested in understanding what are the things that determine post-surgery outcomes, like people who stay in the hospital for too long or other kind of recovery-related outcomes. And there are some fairness considerations that were of particular interest, especially related to gender disparities, although I'm not really going to focus on that in this talk. I'm going to sort of give you instead a kind of a broad look into this kind of adventure in applied causal discovery in this domain and sort of what the challenges were that we faced and how we went about it, which I think hopefully will be useful for future adventures in applied causal discovery. So this is joint work with a big group. Jaren Lee and Ranjani Srinivasan are the sort of two students who led this work. So they did most of all of the heavy lifting, all the programming, and all the getting the data to work together in a nice way. And then the rest of the group has one other kind of data science person, which is Ilya Spitzer, and the rest is people on the clinical side. So all the rest of these collaborators are heart surgeons or other kinds of clinical practitioners who are involved in the work, and one information scientist, Diana Leho. So this is a kind of collaborative project where our interest was into understanding post-operative length of stay, PLOS, which is how long people stay in the hospital following a heart surgery procedure. Minimizing post-operative length of stay is crucial to providing quality care, and it's linked to various other improved patient outcomes like survival rates, recovery times, other sort of measures of medical success, as well as hospital spending. And so it's one of these variables that is the target of a lot of research because it's one that lots of different stakeholders have a vested interest in improving, and is in fact targeted by a lot of existing what hospitalists will call protocols, or basically policies that are meant to minimize length of stay in the hospital. And our perspective here that we took was that to understand how to minimize length of stay, we need to identify first its causal determinants. Roughly, we need to identify those factors that, if they were manipulated somehow, would shift the distribution of postoperative length of stay. And this is different from just a kind of pure prediction approach to understanding postoperative length of stay, which has been explored in many, many research papers where people have fit various prediction models, whether they're simple linear regression models or more complicated machine learning models based on, random forests or neural networks or whatever. But those are all things which aim to predict length of stay well, in some sense of predict well. And they usually are used to highlight some set of key variables that predict length of stay well. But these will provide limited insight into guiding interventions, because as we know from being this, I guess this audience is people who are already interested in causal inference in one way or another, but we know that there's lots of reasons why a variable might be associated with or predict well some outcome, but whether it's really causally related is a bit more complicated. And I wanted to say before I go on that this paper that I'll be discussing it's coming out now in a clinical journal, the JTCVS, which is the Journal of Thoracic and Cardiovascular Surgery. And so it was really aimed at a primarily clinical audience. And so a big challenge in doing this work was how to communicate these concepts, which are pretty foreign to people in this space, in a way that they can understand and that can be seen as useful and as potentially used in future work. So we're not really proposing any new methodology here. We're using algorithms that have existed for many years at this point, but we're trying to sort of create the case for the usefulness of these tools in a way that clinicians can find their value and understand. So as a kind of graphical overview of what we do in the paper, we're using electronic health records data, EHR data, from the Johns Hopkins Hospital, which is where everybody on the team has been working. So we're going to select variables based on clinical expertise. Basically, the doctors that we work with select a kind of big set of variables. I think in the end we had 30 to 40 variables that we're sort of interested in, that have some unknown relationship among them, but some hypothesized relationship to postoperative length of stay. We're also going to incorporate clinical domain knowledge in a way that I'll get into in a second, and sort of combine those things into a graphical learning procedure using the FCI algorithm. And I'll go into what the FCI algorithm is also in a second, but it's a causal discovery procedure that learns a graphical representation between these variables, allowing for the possibility of association due to confounding. So you see these double-headed red arrows on the picture represent association due to confounding, and then the blue arrows represent causal pathways. And so most of the work goes into this left-hand part over here, where we're trying to select the variables, incorporate domain knowledge, and learn a graphical representation. And then once we have that graphical representation, it can tell us some qualitative things, namely where pathways exist between the different variables that we're interested in. But we can also try and use it to start learning some quantitative things, estimate some causal effects. And we use the LV IDA algorithm, latent variable IDA algorithm, which is just an approach to estimating average causal effects, the ACE, for some of the variables of interest on our outcome of interest, was just postoperative length of stay. And we do this as making some additional assumptions about linearity and so forth, which I'll get into in a second. But it's basically a way of starting to translate this qualitative graphical representation that we learn from FCI into some estimated effects, which are you could think of as effects along the edges in the graph. So, so this is a kind of overview of what we're doing. It's basically a pipeline from getting from electronic health records data, as well as clinical domain knowledge, to a graphical representation, and then the beginnings of some quantitative summaries of that graphical representation. So I'll first discuss the data. So we're using electronic health record data on cardiac surgery procedures from the Johns Hopkins Hospital. Johns Hopkins is a major hospital in Baltimore, Maryland, in the East Coast of the United States. And we focus on data in their electronic health record system between 2011 and 2016. And we constructed a kind of cohort to focus on, which was adult cardiac patients who underwent either an isolated CABG, which is a coronary artery bypass surgery, or an isolated valve replacement procedure at Johns Hopkins Hospital. These two surgeries, so there's a lot of different surgeries that people can go through in a cardiac department, and these two are kind of often grouped together as being the two most common major heart surgeries that would happen at a big hospital like this. But we exclude other kinds of surgery, so we exclude things like heart transplants, for example, or other more minor surgeries that might be less invasive because they would have a kind of different patient profile. So we look at these two kinds of surgeries. Very importantly, we limit our analysis to patients who survived to discharge from the hospital. So people who had surgery, stayed in the hospital to recover, and then went home eventually. So meaning that we're excluding patients who died in the hospital. And this is an important aspect of our analysis. In some sense, you might say that this limits our analysis to a kind of selected population on the people who were healthy enough to survive the surgery procedure, which is true. Fortunately, there are very few people who died in this kind of cohort in this hospital. It's a pretty high quality hospital, so there's a relatively small number of deaths, but we do want to treat those separately from our perspective, because the factors that are relevant to survival in cardiac surgery can be quite different from the factors that are relevant to postoperative length of stay. And the postoperative length of stay for people who don't survive can be quite different. So people might have a very short postoperative length of stay if they die immediately after surgery. And that might make them look, like a good case in some sense because they have a short postoperative length of stay, but obviously something else went terribly wrong if they were to die. And so we want to treat them separately. The relevant variables that we chose were identified by our 4 clinicians. Basically, we asked them all to list factors possibly relevant to postoperative length of stay, and then we took the union of those factors. So we basically just asked them to list everything that they could think of that might be relevant to postoperative length of stay, and that which would have been captured in the electronic health records, and we took all of those variables on board. And an important thing to highlight is that electronic health records are very difficult to deal with in practice, often are very messy. But the data that we were able to construct, sort of put together with this team, was exceptionally clean. And the reason is that it didn't come directly from the hospital, but it came from the hospital through this, what is called the STS Adult Cardiac Surgery Database. STS is the Society for Thoracic Surgery. And they kind of curate this database. It's a national society that sort of takes data from local hospitals and curates it into a kind of more clean and uniform form. So the variables have kind of uniform names to things, and there's missing data is really minimized in this setting. So we were able to sort of construct a kind of what looks like a cohort study, in that it's a very clean data set, has very little missingness. We had one variable, which I'll mention, which is ejection fraction, that had some missingness. We did a brief missingness analysis to see what might have been associated with missingness in this variable, but found that it was pretty random as far as we could tell. And so we just dropped the patients with missing values on this one variable, which was only 94 patients in the end. And we otherwise had pretty much no significant missingness in any of the variables that we analyzed. And so after we went through this approach of paring down a data set, our final sample size was 2,610 patient visits over these five or 6 years in the hospital. And we wanted to incorporate what we do know from our clinician collaborators. So in addition to the selection of variables, which comes from the clinical background knowledge, we also incorporate some information about the relative ordering of different variables in the study. So we have variables that are clearly baseline patient level features, which includes like demographics and medical history of patients when they come into the hospital. And then we have things that happen during the operation, which is called intra-op variables, and things that happen after the operation, which would be called post-op variables, all of which follow this kind of ordering of baseline before intra-op things, before post-op things, and before the final outcome, which is postoperative length of stay. And we also know the relative order of a few other variables based on their definitions and the timing of measurement and clinical experience. So for example, within the intra-op variables, we have some ordering information about how for example, the total duration of the operation procedure is something that is causally downstream of the perfusion time. Perfusion time is how long somebody is kept on pump in the operating room. Basically, how long are they kept on the machine, which is pumping blood through their body, is a major factor in cardiac surgery. But this is not something which this is something which could make the procedure overall take longer, but not vice versa. So we could have some sort of relative ordering between some of the variables, even within one of these main kind of tiers of time ordering. And so we needed an approach that would allow us to incorporate that information. But knowing that information, there's still quite a lot of unknowns. So although the clinicians have a reasonable idea of which factors might be relevant, they're quite uncertain about how really they're related to each other and how they're related to postoperative length of stay. In particular, there was an interest in possible mediation or pathway relationships among the variables. Does, for example, extubating a patient in the operating room directly affect postoperative length of stay, or does this effect operate through something in between, for example, post-op complications? Or what mediates the effect of intra-op blood transfusions on postoperative length of stay? These are all kind of mediation or pathway questions, very relevant to the talk that Razi just gave, where they were interested in specific causal pathways along, specific effects along causal pathways for fairness reasons. There's also uncertainty about which variables should we adjust for when estimating the effect of some factor on the outcome. So which variables act as confounders and therefore should be adjusted for, versus which variables might be along the causal pathways and therefore should not be adjusted for because that would adjust away part of our causal effects. And then uncertainty about unmeasured factors. So even though our collaborators gave us a long list of variables to consider, there's clearly the possibility of unmeasured confounders. And so we had to be able to take that into account. So the way that we do this is by learning, first considering that our data came from some unknown causal DAG with arbitrary unmeasured confounding variables. So in this picture, this is a kind of causal DAG where the X's are some of our clinical features that we think might be relevant. Y is our outcome of interest, which is postoperative length of stay. And the U's are the unmeasured, possibly confounding variables. So we're basically assuming that there's some unknown causal DAG over some superset of our variables, which represents the system under study. And since we've had a bunch of causal talks already, I won't belabor this, but it's a causal DAG in the sense that we're interpreting the edges to have a kind of causal interpretation, roughly that an intervention or some intervention on some of the clinical features, if there's an arrow from those clinical features to the outcome of interest, then we think that those may possibly change the distribution of Y. And missing edges in a causal DAG reflect conditional independence, which is our primary kind of thing that we're using to learn the DAG in the first place. So I won't go into this formally, but we can associate a non-parametric structural equation model or a potential outcomes model with this kind of DAG, and that model will reflect, possibly what causes which variables are related to the outcome of interest, but also will imply some independencies, conditional independencies, which are testable implications of the DAG. So this is a kind of a summary representation of this DAG with unmeasured variables with the U's. We're going to, because we only have data over the X's and the Y's, the clinical features and the postoperative length of stay, over just the observed variables, this implies a kind of mixed graph, which has bidirected edges that have double-headed arrows here that represent unmeasured confounders. So these are dependencies induced by the unmeasured confounders U's, U1 and U2, over the observed variables. And even with allowing for these possible, arbitrary unmeasured confounders, distinct graphs will imply testable conditional independence constraints on the observed variables. And we're going to use those testable conditional independence constraints to narrow down a set of graphs that we think are consistent with our data. So this is what's called constraint-based causal discovery, where we basically sequentially test a bunch of conditional independence facts in order to learn a set of graphs that are at least not rejected by our observed data distribution. The way that we do this is by using what's called the FCI algorithm, which in the end will learn what's called a partial ancestral graph, a PAG, which represents an equivalence class of these mixed graphs with possible bidirected edges to represent unmeasured confounding. So the kind of sketch is that if you start off with a DAG that includes latent variables, and you sort of project out those unmeasured variables, and you get a mixed graph representation that includes these bidirected edges. And then you look at the set of graphs that all imply the same conditional independence constraints, which is called the Markov equivalence class of those graphs, of these mixed graphs, that's represented by a PAG. So PAG is going to be this object that contains a variety of different kinds of edges. It contains directed edges, which represent a causal ancestral relation, a causal path from X to Y. It contains bidirected edges, which represent unmeasured confounding. And then it contains these edges that contain circle marks, which represent uncertainty about one endpoint. So this means that it might be a directed edge, or it might be a bidirected edge, or this says that we're really uncertain about all the possible options. And those are the kinds of edges that our ultimate graph will contain. It's called a PAG. And so we use the FCI algorithm to learn a PAG. The FCI algorithm is, at this point, a kind of old classic procedure that was developed in the late 90s, including by Thomas, who's here on the call, but was developed to basically as a constraint-based conditional independence testing approach to learning an equivalence class of graphical models when you have unmeasured confounding. It also deals with another issue which I'm going to ignore, which is selection bias, but we don't deal with that in this discussion. And the way that FCI works, if you're not familiar with it, is roughly that it begins. It's a procedure, it's an iterative procedure that begins with a complete graph with only circle edges between connecting every vertex to every other vertex. And then it executes a sequence of conditional independence tests. Basically, it looks for variables separating sets S, that if you find some conditional independence holds for some S, that means that we can remove one of these edges. And then it orients some of those edges by looking for unshielded colliders, which is similar to the kind of classic PC algorithm. It has some additional steps that deal with these kind of longer paths that are inducing associations with due to unmeasured confounders, and additional orientations that follow from the rules of a partial ancestral graph, which I won't go into here. In the appendix of my slides, I have the full algorithm sort of spelled out. But basically what you should know is that it's executing a sequence of conditional independence tests to remove edges, and then orienting things based roughly on finding colliders, which are these special substructures where two variables collide at a third variable, and that gives us some orientation information. And so we use this algorithm in particular because it allows for unmeasured confounding, and it also allows for us to incorporate the aforementioned clinical background knowledge. So we can restrict the conditional independence tests and the orientation rules of FCI to respect this ordering, where we know, as I said earlier, that that baseline patient features sort of precede intra-op variables, which precede post-op variables, which precede postoperative length of stay. So we incorporate the background knowledge in the algorithm directly. We have this practical challenge, which is that our data is a mixture of continuous and categorical variables. Some things are measured on a continuous scale, and some things are discrete. Like, for example, we have a variable which indicates which surgeon did the surgery. So we have like 4 or 5 discrete categories for that designate which surgeon it is. We have other discrete categories like, was this person extubated in the operating room, yes or no? Were they re-intubated sometime later after surgery, yes or no? These are kind of binary variables, but we also have continuous things, which include various biomarkers and the length of the operation and things like that. So in order to do conditional independence testing with a mixture of continuous and categorical variables, we use what's called the degenerate Gaussian likelihood ratio test, which basically is a parametric test that assumes things follow a degenerate Gaussian distribution and uses the likelihood of this degenerate Gaussian distribution to set up a conditional independence test. We also had to do make some other practical choices. For example, we have, I think it was around 40 variables in the end. And when you start conditioning on subsets that are really large, so if I have to do these conditional independence tests where I condition on subset S, conditioning on too many variables at the same time leads to very low power. So we had to limit the size of the conditioning set to make sure that we had relatively reliable independence tests. So I think we limited to the size 3 or 4 in the study. And then we also, we have to choose a threshold for what counts as a significant test of independence. So there's this tuning parameter, which is how much dependence means zero dependence for the purposes of our conditional independence test. And we explored the sensitivity of our result to varying the significance level, this tuning parameter, to different values, and found actually, fortunately for us, that it was pretty robust across different alpha values. So we chose the alpha equals 0.05 level as our kind of main analysis, but we have in the supplement to our study, we have the results for different values of this tuning parameter. So the kind of results that we get are these really messy graphs that are hard to look at. So this is one representation of what we learned that tries to sort of combine edges together in order to make the graph a little bit easier to look like. Otherwise, it really looks like a big mess of arrows. So the way you read this kind of representation is that the variable that we're interested in here is postoperative length of stay, which is up here on the top right corner. And the pathways from these different variables sometimes will get sort of grouped together into combinations of pathways in this graph. This is a bit hard to read, so I think the better kind of visualization is to view the graph as a matrix. So the matrix is one where we can see for every pair of variables what kind of edge is between them. These are really both kind of complementary representations of the same result, but this lets us sort of quickly identify visually what are the variables that have a directed edge into postoperative length of stay, and it's almost all of them. And then which variables are connected by these bidirected edges, that's the red, and then which edges edges exist between the other variables themselves, which might be these blue directed edges or these purple partially directed edges. And this kind of lets us read off the graphical representations. So what do we learn from this procedure? Well, we were able to estimate some causal effects. So I won't go into how we did this, but we assumed a linear model and then estimated the causal effects using the backdoor adjustment. So basically using the graph to determine which variables satisfy the backdoor criterion, and then running a regression of the outcome on the exposure of interest with that backdoor set, and we get an estimate of the average causal effect that way. And we can see that there's some stuff which has a quite large causal effect, which would be expected, like having complications post-surgery are all things that we know would have a large causal effect on the length of stay. But then some other things which are less obvious, like the use of blood products in the after surgery or during surgery, extubation in the OR, and reintubation. These are the kinds of things which are more controversial. And in the paper, we compare the effects estimates that we get from the backdoor criterion to using regular linear regression. And we also identify some mechanisms of interest doing a kind of really rough mediation analysis, again, based on a linear kind of model assumption. So we look at a few factors that were of particular interest to the doctors, in particular, extubation in the OR and intraoperative blood products, and found that there are some interesting kind of mediation relationships where extubation in the OR has an overall effect on postoperative length of stay, but a big chunk of that effect really comes from the subsequent likelihood of reintubation post-operation. And this is of interest because it means that extubating in the OR is actually good if we can do it. It's good for the purposes of reducing postoperative length of stay, but it is bad if it leads to post-op reintubation, which is the kind of real problem. And similarly, for intraoperative blood products, we have these kind of rough mediation relationships where there's a direct effect of intra-op blood products, but then there's this kind of mediated effect of post-operative blood products, which is also of interest to the clinicians. So since I'm out of time, I'll just summarize the results and sort of the lessons that we learned. Most of the factors identified by the clinicians were found to be causal determinants, whether they were indirect or direct. And the sort of indirect and direct and mediation relationships were really kind of interest here. The estimated causal effects were often of a different magnitude and sometimes of a different direction compared with just the naive regression approach, where you condition on everything else in the data set and look at regression coefficients. And this makes sense because as we know, conditioning on everything else means that you're conditioning on some variables were potentially on the causal pathway between the exposure of interest and your outcome, whereas using the graphical approach, we can identify the backdoor set to condition on. We identified some very possible mechanisms of interest that warrant further study. These are very tentative kind of conclusions because they're based on a linear model that is very likely unrealistic in this setting, but they give us some further things to think about. And we hope that this kind of pipeline that we produced will become more normal in data-driven generation of hypotheses about mechanisms in this kind of electronic health records space. We faced a bunch of methodological challenges.
Sorry, Dan, we have to stop.
Okay, so this is the last slide, just some methodological challenges about the work, and I'll wrap up with the citation here. Thanks. Sorry for going over.